Okay, good afternoon everybody, and welcome to the first of Low Carbon Building Gateway seminars, which we are running together with Kickstart Online project. Welcome everybody who already joined us, and let's not delay the start now. So the webinar title today is Solid Timber Systems Nail and Dowelled Plank, presented by Deb Turnbull from Edinburgh Napier University, David Blakey from David Blakey Architects, and Neil Sutherland from Neil Sutherland Architects, and Makar from Inverness. First of all, I would like to say a few words about Low Carbon Building Gateway project for those of you who doesn't know too much about it. The project commenced on 1st of July in 2010 and going for 3.5 years in general till the end of October this year. The targets of the project are quite big, and we're supposed to reach 1,000 organizations, create 20 supply chains, and start at least 40 new research projects, and work with different companies here in Scotland to develop new products and systems for new built houses. This project is going quite well. The current outputs, as counted by the end of 2012, showing that we assessed 260 products. That is approximately 87% of completed project, and we still have 10 months to go. In general, the project divided into two halves. Phase 1 is to do the assessment of the prototype or idea of the product, and then phase 2 is actually to go and install it into real houses or into innovation park, to which we have link here in Scotland with BRE Scotland. So the presentation will be made today would be about the structural project which was run during the LCBT Gateway project. So in total we have done quite a substantial number of projects, and so we chose 3 of them to go with. So the first one today is about the structural problem sorted or solved with our structural experts. So now I'm pointing out towards Deb Turnbull from Edinburgh Napier University, who will talk us through this fantastic project which we have done.
Good afternoon. With today's presentation, we have 2 related research projects. We have the 2 different people involved, 2 different SMEs. The first was with David Blakey. He's an architect in Edinburgh, and he was developing a central serviced core system, which he calls the E-core, and it was built with homegrown nail lamb, or sometimes called Brett Staple. This was made with wall and floor panels. And the second is related to dowel lamb, which is also called Brett Staple, and that was in conjunction with Neil Sutherland and Makar up in Inverness. Now, we've got several different sections of this. Neil and David have both been pre-recorded, and they'll present a little bit to camera, and I then will follow on with the technical research of the different projects which have been put together. We first start with David Blakey, the architect on the E-core project. We have some slides which show various projects on which he has been doing this, and he is doing some talking through them as well. So I will pass you on to David.
I'm David Blakey. I'm an architect in private practice in Edinburgh. We generally deal with relatively small-scale domestic commissions. However, back in 2008, we were lucky enough to win one of the plots at Scotland's Housing Expo. And within that, we developed 1 or 2 concepts, which, and while unfortunately we weren't able to take to their absolute fullness at the time, following that, we formed a collaboration with Napier University and developed some of those ideas further in a more technical version. The primary aim was a central service core for the house, something which could be constructed off-site in a very efficient way and brought to site, stacked up this service core was also a structural element, so it provided structural racking to the building. At that time, we weren't really aware of the technologies that were required to allow that to happen. So in collaboration with Napier, we started working on the actual fabric that the external walls of the core would be made from. Because it's not a material that is going to be seen, it's just its technical requirements, we opted for nailed stack plank rather than what's widely recognized as cross-laminated timber. It's a solid structural material. It's less expensive. It's less visually perfect than cross-laminated timber, but that wasn't a requirement for this particular project. Cost, serviceability, availability were the important things. That led us on to a series of investigations with Napier into the structural qualities of nail stack plank. We carried out a series of tests across at BPAC in Fife, which is a test facility across there. So we had some test panels of nail stack plank. Now I should explain what nail stack plank is at the moment. It's taking a relatively low grade, widely available timber and layering it and nailing each plank together to form a larger structural panel. It is available on the continent, or has been available on the continent. I believe there might be issues with that now, where it's much more, the manufacture is much more automated. For the sake of using Scottish timber, we used a small social enterprise in Fife to create stack plank panels for us that were then tested, and Debs will no doubt talk to you more about the sort of the tests that were carried out and the results of those tests. But what it led to was it was the ideal material for us to use on the external walls of our E-core units. At the same sort of time that we were beginning to look at the nail stack plank leading on to the creation of the E-core, an opportunity arose to collaborate in a project across in Fife that was called the Fife Housing Innovation Fair, which was run by Kingdom Housing Association. And this was the next step from the Housing Expo, but it was looking at it in a much more simple way. They were looking at the technologies of the houses rather than the design content of the houses. So we were very grateful to have been selected as one of the partners for the scheme. And it meant that we could then move on in a live situation with funding from the Housing Association to actually implement the ideas that we've been putting together. We formed a collaboration with Napier University and Craft Architecture in Glasgow, who was developing an external wall panel which meshed very beautifully with E-core. We designed the specific E-cores which satisfied the Housing Association's requirements, and we then went on to have them constructed again, with a variety of manufacturers in actual fact. The nailed stack plank, all of it using Scottish timber, were manufactured by Neil Sutherland up at Macker, Springfield Housing up in the northeast, and also Living Solutions in Fife. These were then constructed in the workshops at Living Solutions and fitted out before being taken to the site and constructed. It was all very interesting, and it was innovative for us at the time, and it still is innovative. So we called our house system Future Affordable, and it's currently being tested for all its efficiencies across there by I think Napier that are involved in the testing of it. The e-cores themselves have got many benefits, of which we hoped they would have, and we discovered as we went through the process that they had. The intention is that the e-core itself is fully fitted out with all the technology that a house requires, and it's meant to be kept simple. I think houses can become too complicated these days, especially social housing. It needs to be kept simple so that the operation of it is it's not difficult to achieve the efficiencies that the system is meant to achieve. So it incorporates whole house ventilation. The way that the house is designed, it allows it to include all the heating and drainage and hot and cold water pipework, so for a very simple connection once it arrives on site. It's got all the services installed in it for the kitchen. It's got all the control gear for whole house ventilation, the heating systems, any micro renewable systems. In Fife, we incorporated photovoltaics onto the roof, so all the control gear for that was built into it. All sanitary ware fitted. Very simple. All the sort of the technical aspects of a house are included in the e-core, built off site, so that their installation quality is high, and brought to site. And it means that there are far fewer tradesmen required to travel to the site itself. Prefabrication, off-site, higher quality, factory conditions. It's just the way that we believe that future housing should be constructed. The benefit of using the stacked plan car, carbon capture is important. Each pod that we installed in Fife has 1.2 tons of carbon captured in it for the length of its life. It provides thermal mass in the heart of the home. It provides structural solidity to the house as well, which means that in transferring the lateral loads to the floor plates, there can be less timber in the external structure, which means you can have more insulation in the external structure, less thermal bridging, so that the whole thing works together to create a more efficient house building construction. We're currently looking at how using 2 tons of timber in the centre of the house can improve the internal air quality. The jury's out on that one at the moment, but it is something that we believe that there is a benefit to the house in. When we first had the idea of a timber-built central service core for housing, we really weren't sure where to go with it in the first place. We spoke to Edinburgh Napier University, who put us in touch with the right people in the Centre for Innovative Construction, and it all took off from there. Breadth of expertise, breadth of knowledge, second to none. We couldn't have got to where we are today with e-core without their help.
Thank you, David. We're next going to show a short animation of the e-core as it fitted within the buildings that he built up in Fife, which lasts about a minute, and that will now follow. Okay, we now have a few short clips of film which explain some of the processes we went through when we were constructing the nail lamb and also the dowel lamb that we come on to later on in my talk from the workshop up in Makar. We're in Makar's workshops up near Inverness. We're doing a grading session on some sideboards that we're using for the Brett Staple panels. The process is that we put the sideboard on the weighing scales. They isolate it from the structure it's sitting on, and they weigh it because we need the density to actually calibrate the measurement that the machine gives. Because the sound wave is affected by the moisture content of the timber, in order to correct the grading for the correct moisture content for a batch of timber, we have to take moisture content readings. In this particular case, 14.3. We were aiming for 14% plus or minus 2%. We have the Brookhouse handheld grader. The handheld grader has a standardized hammer built into it, so you press the button, it hits the end of the piece of timber, and the sound wave and the frequency is converted into a stiffness, and there are various settings as well that can be used, but there are no settings as yet for Sitka spruce, which this timber is. So we do this for all the materials, and they're numbered so that you can tell where they are in the panel when we do some testing. This is a typical joinery press for making doors and windows, and the planks are stacked up on the frame. Then they're clamped into position using the hydraulic rams. The drill is often on a manual sliding arrangement that was manufactured by Neil, and it's drilled in at 300 centres. It has to be knocked in a little bit with a hammer, and then you can press them in with one of the rams before then the whole process just gets moved along and drill the next one. These ones are using beach dowels, and we're hoping that maybe in the future we can get a bit more automation going on these sort of things. It's quite a labour-intensive method, but this is how all the European manufacturers started. Okay, we now have a short section by Neil himself talking about Makar construction and the ethos behind his work.
Welcome to Makar. We're on the edge of Inverness and standing beside our workshop facility. The workshop itself was built by ourselves last summer. It uses only Highland timber in its construction, both inside and out. We use this facility to make panels and other structural frames for our houses. The idea being that we make more or less everything inside, so we can work in all weathers and all seasons, and then we take the completed components out and we erect buildings very quickly. Normally we can build a house in between 2 to 4 days. An example of the materials that we're using is this birch here, which has been planked, and the intention is to use this for the production of dowels. Up till now, in putting our dowel lamb together, we've had to import dowels from Germany or Switzerland, and which was fine as far as it goes, but what we're keen to do now is source the two main materials from the Highlands. So we've cut these boards. They'll be cut into roughly 25mm squares, and then we'll form them into dowels through a spindle moulder. One of the reasons that we're interested in this whole timber product development and the dowel lamb in particular is to look at the materials we have and add value to them. So we have, for instance, we've got hardwood materials in Scotland which are generally, not always, but in many cases wasted, and we could actually be using them for a higher grade of purpose. Our investigations into the way the Europeans have developed products is that the development of a laminated product like this with dowels has gone hand in hand with progress with off-site construction techniques. Now, MACAR is interested in assimilating some of this material so long as it makes sense to do so in our construction process. So we're investigating this at the moment, and the idea is to integrate it directly into the way in which we're building. So we're keen to look at that. One of the reasons that we're able to undertake this work is with the support of Edinburgh Napier University and the Centre for Off-Site Construction and Innovative Structures. Without the support of the centre, it'd be very, very difficult for us to progress this type of work. We've noticed in our travels in Europe that type of arrangement, where you have a university and a private company working together, is the norm in Europe. And I think what we're doing with Edinburgh Napier is an example of universities and companies working closely together for a common purpose.
Thanks. I'm now going to actually start my presentation, which is going to cover the technical aspects of different sorts of research. I'm going to cover both nail lamb and dowel lamb, both from homegrown timber. So we've asked before what actually is nail lamb and dowel lamb, also known as brettstaple. Nail lamb started out, and it was where you can see on the drawing on the top right there that there was just planks laid next to each other and just nailed together into a massive panel. That was experienced some difficulty with post-processing, and so that then the dowel lamb came together by then connecting a section of dowels clamped together and then drilled all at once, so that the dowels hold everything together. Mostly the manufacturers at the moment do perpendicular dowels, but there's also one company which produces the brettstaple with dowels that go diagonally, and they believe that this makes the whole panel more stable. They can be used for wall, floor and roof elements. The picture on the right just shows a typical make-up that they do in Germany, whereby you have the panel which is on the left and then a thickness of insulation which is typically cellulose or wood-based on the outside. All of this research was had several sections to it. We wanted to actually look at the availability and the suitability of the resource that we have here in Scotland, various ways of looking at the manufacturing, and then of course what are the physical properties. Engineers need to design with it, and architects need to be familiar with it as well, and also we were able to then incorporate the nail lamb into the e-core that David has mentioned just beforehand. So we did various test programs. I'm going to talk first of all about the nail lamb, and then go on to talk about the dowel lamb afterwards, although because some of the testing we did was different, even though we end up with a similar project. For the both different projects, we were using the handheld grader which you saw in the film, and we were doing this to obtain the acoustic MOE, or modulus of elasticity, which is the stiffness of the piece of timber, which you can relate strength and other properties to. Then with the nail lamb we did lateral load tests on aluminium nails, because with using aluminium nails it means that then you can post-process without having to replace saw blades all the time when you start hitting the steel nails. We also compared that with steel nails from just published values. Racking tests, these were the main part of the test that we conducted, because you really need to find out the strength and stiffness of the racking panel compared to the open panel, which we're all familiar with. Next series of tests were 4-point bending tests, which were just loaded across the full width so that we could check the MOE acoustic grading results. And finally, we also carried out some 3-point bending tests of full-size panels, which was going to be used to investigate the load spread sideways under point loads, which is just required under EC5 design guidance now for floors. So we're starting off with the resource. For the nail lamb, we actually used standard C16 timber that was supplied by various sawmills, and the different companies that David mentioned were making up some of these panels for us. They were dried to 16% in dehumidifying kilns at various places. I've just said Living Solutions there, but we also had some dried at Makar as well. And 16% is required because we don't want the material to shrink too much once it goes into a building which is then heated to 20 degrees. And this was a common percentage moisture content that was used in the continent as well. So as part of the grading process, we identified all the boards so that we could then check where they were in the panel so that we could relate one stiffness panel to the actual individual pieces of timber that we were measuring. For the nail lamb project, we actually used the Hitman HM2000, which is the machine you see on the right there, the yellow one, that you just have to hold against the end of the timber, similar to you saw in the film before, but this particular one you have a separate hammer which you have at the end, and what they do is that they measure the sound wave as it goes up and down the timber, and then the stiffness of the timber is directly proportional to the velocity squared and the density of the material. So you can see that the velocity changes depending on the moisture content, so you have to correct for the moisture content as well. There are various settings that you can get for various timbers, but in this case we were just using it with the actual density and the velocity reading to get a direct stiffness. And the same, as I said before, we are actually testing them against the full-size panels further on in the project. So going back to the other testing then, we've got the nail tests. We wanted to use all aluminium nails, and these are the 3.1 by 90 annular ring shank nails, which give better performance, and we were comparing it to a more standard steel nail, which is used typically in timber frame construction. So the various properties that we were looking at was the yield moment, which is the strength, and that could also be found by doing the tension capacity, because they're directly related when it comes to how the joints behave. And then you have the head pull-through parameter and the point side withdrawal, which also affect the strength of a joint. And then finally you can do the whole shear test and to actually relate all of those together. So you can see from the test results that the aluminium nails perform much better than the actual EC5 predicted, and actually much better than the steel nails theoretically, and also a little bit better in terms of the slip as well. So we were hoping then that we would get better results from the aluminium when we looked at the whole panel compared to the steel. We shall see. So we come on to the actual panel manufacture. This is a very straightforward process. All the manufacturers made up jigs. Makar decided to do a double-sided one, and they were just stacked one on top of one at a time, and then each layer was nailed on separately. We had templates to actually show where to nail, because they were slightly longer than just two boards, so we wanted to make sure they were slightly staggered, and they were just all nailed together with a standard compressed air nail guns. One of the issues we did find is that we were able to make up some aluminium panels, was that particularly in the Sitka spruce the knots are so dense that we did have difficulty with some of the nailing, as you can see. Now, the first main test we carried out was the racking tests, and these were put together with a solid panel, but the OSB sheathing was nailed on in exactly the same way that it would have been on an open panel, so we could get an idea of the difference in strength between the open panel and a closed panel. The only difference being was that the open panels that we were comparing against were 2.4 by 2.4 panels, and ours were very slightly shorter. So hence you can see that the results on the graphs there are normalised to just a kilonewton per metre load. In this particular case, the individual panels, because there were 4 or 5 panels in each overall 2.4 panel, they were fixed together with screws, and then there were standard nailing fixings between the verticals, the stacked plank part, and the sole plate. And we also compared it with the theoretical method that's been developed, also with the help of the Centre for Off-Site Construction, which is the PD 6639. Now, if we look at the graphs, you can see that each individual group, on the left-hand group of 3, this is with no vertical load, and the 3 on the right have a vertical load of about 10 kilonewtons per metre vertical load. The left-hand side, you can see of those 3 actual test groups, that the blue is the test load, the red column is the theoretical maximum load according to the PD, and then I've also added a third column, the green column, which is the actual test load at a typical serviceability limit of deflection at 0.003 of the height of the panel, which is 7.2 millimetres. So if you look at the open panel first on the left, the middle one, you've got a nice relationship there in that the maximum load is the highest, then the theoretical load is a little bit less, and then the load that you want, the serviceability, is less again. But if you look at the 2 different solid panel ones, the one on the left is the 9mm sheathing board, and on the right it's the 11. The open panel one was in fact just 9mm, so it's the 2 left ones are directly comparable. We have a much stronger panel, but also the theoretical calculations don't match very well at all. And then when you look at the serviceability load, it's actually, you're getting a greater than the theoretical maximum load. Then when you look at the right-hand ones with the vertical load applied, then it's even more marked that, again, the solid panels, the 2 outer ones, are much stronger at a very high, sort of between 8 and 9 kilonewtons a metre run. You get a similar relationship, though, that the deflection is actually in the sort of region that you would want. But when we come onto the stiffness, it's much more marked, and that when you look at the no-load ones, you've got more with the 11mm sheathing than you have with the 9, which is exactly what you'd expect, but it's only just a little bit stiffer than the 9mm open panel, which is quite surprising, because you've got all that timber to actually slide across one another to actually get the deflections. But when you look at the vertical load graph, it's even more marked, with the open panels appearing to be an awful lot stiffer than the solid panels, and in actual fact this wasn't the case. What happened was that because the panels were much stronger, the region of the load deflection graph that you use to calculate the stiffness, it's skewed further away from the initial deflection curve, and the curves, it rapidly tails off. And so although the load deflection curve of all the panels are quite similar at the low deflection levels, the strength then skews it. So I think there's definitely scope to actually look at how you would need to check and use the test methodology to actually work out a design value, because that's still not, it's not really well geared to a solid panel at all, which is hardly surprising because it was worked out on open panels. And you can see from the photograph that, again, it's the leading stud that causes the problem with racking panels. So if we move on to the bending tests, this is, as I said before, we were going to, for verifying the acoustic grading against an actual physical bending test, we got a very good relationship in actual fact between the bending stress and the stiffness, which you often don't see in Sitka spruce, but this was quite a good relationship. The only worrying aspect of this was that we ended up with quite low E values compared to what we were expecting, given that it was indeed bought straight from the sawmill as graded timber. But when you look at the actual strength of the panel, the stress in the timber, it was a very good value. We only tested 6 in each panel, of each panel type, and so the mean is very much higher than you'd expect from a piece of C16, but even the characteristic load, which is normally penalised for having just such a small sample size, is still up in the C16, which was quite interesting. One point to note about the test that we conducted was, because you've got so much timber in the floor panel, we increased the span to depth ratio, whereby you would get a sort of typical 12 to 14 millimetre deflection, pretending it was a floor, which then means that the shear deflection, which is related to the span, is an awful lot less. And in fact, when we looked at the difference between the local E value and the global E value, which include the shear, there was very little difference at all. It was only in the region of a couple of percent, and one was one way and one was the other way. So it's not such an important factor to take into account then. One other thing on the strength, and bearing in mind that a 600 millimetre wide panel, say comparing that to where you have joists at 600, you've actually got a lot of planks in one panel, about 14 planks would make up a panel 600 wide, and because of course they're all fixed together, then they're going to increase the strength, and EC5 actually allows for that by allowing you to increase the stress by 10%, and that again, say, was shown by the test results. We come on to the 3-point bending tests, and so we were going to compare the difference between the two different nail types, and we actually had panels both with steel and with aluminium nails for these tests, and it's a good way of working out the lateral load spread for when you have to put a point load onto a floor. And the EC5 method now for floor spans actually require you to look at vibration, and part of the testing for that is a point load and how much it spreads through the floor decking laterally. So when we looked at well, also we did some with OSB and some without, just to see what the difference the OSB made, and that was about 5 to 10% difference just by adding the OSB, because obviously it spreads the loads. When we look at the actual deflection between the centre and the edge, you can see it's quite marked, and in that particular case, the excuse me, the higher the ratio between the centre and the edge, obviously the less load spread you get. And so you can see in this particular case, even though the aluminium nails appear to give better values when we were just checking individually, in actual fact it was the steel nails that performed better than the aluminium. And again, when we looked at the difference in load spread, we actually ended up with very similar strength with the central boards, and on all these fails under the centre. That was it for the nail lamb part of the programme. I'm going to lump all the conclusions together at the end. So if we come then onto the dowel lamb test programme, again we used the same acoustic grading techniques, but except we're using a different machine. The whole point of dowel lamb is that the boards are dried down to a low moisture content to avoid this large shrinkage aspect of when it's into a building. But during manufacture, and of course for floors as well, the dowel's actually used to lock the panels together so that you can physically move them around. And as a result of that, you need the dowel as dry as possible, and it's typically it moves a certain amount, and hardwoods will move more than softwoods, and they all have different amounts. So we were going to look at the different sorts of hardwoods that are available in Scotland to see how they compared to theoretical values and whether they'd be sufficient. And then we carried out various tests on actual connections based on either the friction of how to choose which dowels might be better to use, and also whether anything split or any difficulties we had during fabrication. And finally, we carried out some bending tests of full-size panels just to see how they performed and to compare against the acoustic grading. So if we look at the resource that we used for these particular tests, we were using the sideboards, which are the first to be removed in the sawmill, and typically they're used for fence posts and pallets, but they are in fact typically stronger and stiffer than the boards in the centre of the tree. You can see as it goes towards the centre of the tree, then you get less quality. So we were using two different sorts of timber here. We had Sitka spruce and Scots pine, and these sideboards were then sawn down to out of 22 by 100. So, and then for the dowels, as I mentioned just before, we want a medium or preferably a large moisture movement so they lock together well, and by having a higher density then you get higher joint stiffness as well, and also for the tensile strength gives you a higher strength as well within the joint. So there are the different list of hardwood material that we were able to source. Not very much of it apparently in the constraints of the project. So we actually, for the majority of the connection tests, we just used imported beech dowels. The dowels we used were 20.5mm diameter, and they were fluted, and they were 600 long. So this is the first dowel test we conducted. At the top there we've got the moisture movement. So you can see that that beech has the highest movement of all, and of the two columns that we have there, the left-hand one is going from the fully dried state at 6% to a service class 2 condition, which is not optimum, but it can always possibly happen. But the more interesting one is the 6% to service class 1, which is where we would hope to actually have our dowels working. So you can see there that beech is still the highest, up at around 5% moisture content change. Cross-sectional size for every moisture content change, with the lowest being sycamore, but with ash and interesting Scots pine as well. We'd like to actually investigate whether Scots pine dowels could be used within a Sitka spruce panel, possibly just in a wall where the strength of the dowel itself isn't quite so important during service. So that gave us some interesting readings there. And then we followed on again with the different variations in the dowel species to look at the friction. I have to just explain the graph a wee bit. We've got the red columns are where the dowels are put into Sitka spruce planks, and the grey ones are when it's put into Scots pine. And then the first group of 3 and the second group of 3, it was conducted with dowels of all the same size, but then they were inserted into holes of different diameter. So we have the small hole, medium and a large hole, where the small hole was 1mm less diameter than the dowel. The medium hole was 0.5 millimetre smaller in diameter, and the large hole was the same size. And so you get this, obviously, well not obviously, but as you might expect, that the smallest hole had the highest frictional force requirement to actually put it in, except interestingly for the Scots pine, which was very similar to the medium. And there were 1 or 2 issues with some sample splitting when we were constructing these, so maybe that's the reason why on that one. If we look further over to the right-hand side of the graph, where you've got the different species, so you've got birch and Scots pine were into Sitka spruce planks, and then all the others were into Scots pine. And it's quite interesting how they're all varied. And in addition, we've got the slip modulus model, so how much load you needed to actually cause the dowel to slip through at all. So that might be important if you're looking at how much hydraulic equipment and stuff you might need to push the dowels through. And also what we're hoping to do in the future is, if we can get some more connection tests, is to see whether that slip factor has any sort of correlation to the strength of any shear connections test that we do. Another dowel test we were doing was on the tensile strengths. We compared all the different dowel materials. Unfortunately, because we didn't have very many samples, and we weren't really sure of the quality because they'd already been cut into smaller pieces, they didn't really match up to the published data that we were expecting. In particular, the beach ones, which were very much less than we were expecting. And although we couldn't find figures for tensile strength of small clears for European beach, they look quite disappointing too on the face of it. So we want to do more work in terms of the dowel strength. When we look onto the full-size connection tests, the lateral capacity perpendicular grain is the one that's most important in terms of floors, because obviously when you have a point load, you're spreading the load out sideways, and then the dowels are actually transferring the load between one plank and the next. So we used we've got the graphs there for strength and for the stiffness. We actually conducted tests. This was all done on medium-sized holes because that was what came out as most promising from the individual tests. And you get the highest strength actually with the medium-sized hole, which again was quite surprising. We used a modified dowel strength and used the EC5 equations, and that was based on John Shanks's research when he was looking at oak pegs, and the strength values actually weren't too bad considering that the equations were worked out for steel dowels. But more worrying in terms of how to design something is the stiffness, because although we used the test values for the tensile strength of the beach dowels and the actual measured density of the timbers, we've got much less stiff joints than you might have expected. Part of that is due to the fact that a steel dowel, of course, would not compress in the same way that a timber dowel did compress within the actual tests. So that obviously needs to be taken into account. The other aspect in this particular test was that the planks were only 22 mm wide and our dowels were 20.5, and so there was a lot of rotation in the dowel as well, so that could partly add to that as well. Then we look at the flatwise bending tests. For the Scots pine, it worked out really quite well in terms of the acoustic grading, and we got quite similar results. It was a little low compared to the test result, but that's quite common, that acoustic grading is a little bit low. But the Sitka spruce was somewhat unusual in that the dynamic MOE was really very high, considering that we were expecting a C16 type board, which would have a stiffness value of about 8,000, which is in fact what we got through the mechanical testing, but the acoustic grade gave us a value of 11,800, so that's somewhat unexplained at the moment. Again, on the strength, we got quite a good range of a good strength, even though these were ungraded boards as such, other than the acoustic grading, with a mean strength of equivalent to a C22. And again, the characteristic value, even though we only had 6 tests, it still came out at sort of 16 newtons per millimetre squared. The Scots pine was even better quality, and you can see there that even the lowest strength we got for the panels there was 28, which meant then with just a very small sample characteristic value of nearly C24, which is very promising for using the Scottish timber. Again, EC5 allows this 10% for mechanically jointed beams, so it's a question of can we use dowels to actually use that enhancement, and because of the fact that they're joining lots of different planks together, then I would say that would apply, and the results would seem to bear that out. We actually worked out some span tables, somewhat complicated. This is a bit of a combination between the nail lamb and the dowel lamb, so these were worked out on the EC5 principles, just on standard deflections and bending strength, but also we tried to look at the vibration criteria, for which there is a method, but it's based on open joisted floors, which of course we don't have. So we looked at trying to see whether that would give us comparable values to how the values that they have on the continent for their timber. So if you look at, for the nail lamb, the top group of 3 there on the left, the loads don't quite match, unfortunately, but we've got three levels there with a 0.3 dead load as well as the plank load as a typical sort of basic floor, and then we're comparing it with a 0.5 kilonewtons per metre extra dead load. This is all for domestic loading, and then the last one at a 1.75 dead load, which would be for if you've got a concrete screed on the floor for an intermediate separate dwelling type floor. So you can see there that the spans that we can get compared to the published span tables are not that far adrift, and the fact by increasing the depth of the stack plank by only sort of the next level up of sort of 20 millimetres, we get very comparable performance. And this is using a C16 published table rather than the actual grade of the timber that we got. When we're looking at the dowel lamb, on the bottom group of numbers, these are for a dowelled lamb, but it's using a slightly higher live load. But again, you can see there with a dead load of 1.8, they had a span of 4 metres, and a comparable span for C16 is 3.8 with slightly less load. So it's a bit difficult to compare them. But again, just by increasing just a small depth, we end up with very similar type of performance. So, in conclusions, I've got to split this into 2. We've got the timber and its properties, and I've talked about the other aspects later. The sideboards and the standard size boards that we got from Scottish Timber, they both worked well. We didn't have much distortion in the boards, so there was not much wastage in terms of having to dry it down to that level, which is very encouraging. The acoustic grading worked very well with the Scots pine. We've got a few questions with the Sitka spruce, but we've done it on Sitka spruce before and found very good correlations, so that's a little bit of a glitch on that one. But it's very straightforward to do, particularly so you can do it. If you have a local sawmill, mobile sawmill, that would be able to do this, and it gives very good correlations, say, other than the odd ones we had for the Sitka spruce. In terms of designing with it, the physical properties, you'd use E-mean for the serviceability, which is as you'd expect. We think it would be possible to increase the bending strength by 10%, but there's definitely some more work to be done in terms of looking at the vibrations and how the load spreads across the floor. And on the manufacturing front, we've split this into the nail lamb and dowel lamb because it's quite a different method of construction. The nail lamb was particularly straightforward, very simple jigs, and just somewhat slow, although they're in Europe, in the remaining of unit, there are semi-automated and automated systems whereby they produce them on a main production line. Aluminium nails were good, not quite as good as the steel nails, and we did have problems with the wastage. But in terms of post-processing and using for wall panels with openings, they would definitely be the best sort of nail to use, because you don't want to be trying to saw through planks with steel nails in them. And on the dowel lamb, we had the best results were from our sorry, I'll start again. The best results we had were from the slightly smaller hole compared to the dowel. Another issue in terms of the manufacturing, that as you could see from the little clip of film, the drill was really struggling to get through once we got right the way down through the bottom plank. But this was just really a mounted hand drill. It was only 750 watts. And what happened was, because the auger itself only had a 2-prong blade at the end, it sort of over drilled a little bit, so the edge planks were a bit loose on some panels. But we think a better drill, stronger, and maybe either an auger with 3 blades at the bottom, or on continental Europe the big machines use a compressed air drill which forces the swarth out and much quicker drilling. And the frame press itself was quite clumsy and quite heavy to move around. I think there could be much better variation in how you could adjust that to make it easier to use. And finally, a little bit about the sort of future work that we're looking at. We have got some more projects on the go. We want to extend the use of the handheld grader, and again using sideboards. We're wanting to actually do some more work with different sorts of homegrown timber. We're hoping to use some of the birch that Neil mentioned in his film, and also some sycamore and other materials as well. And using all those different dowels, we want to look at the embedment tests for the dowels and the board material, maybe with different thicknesses as well, and just see whether we can get the slip part of the EC5 much better correlated. And another thing we would like to look at is that when you're looking at that lateral load spread, whether a tongue and groove board, which not only helps to keep the boards level, but whether that will actually help with the load spread sideways. And we're going to be starting that fairly shortly. And since we've started our project and with all the work of the Brecht-Staple network, there are various people who are hoping to set up the dowel lamb production in Scotland and England. So that's very promising. So there we are, and we've got lots more to come in the future. So I think now I shall hand back to Elena, and we can take some questions.
Thank you very much, Deb, and I would like to thank also David and Neil, who are not with us, but who did some presentations. Hope to see some questions from you, but bear in mind that because architects are not here, we might not be able to answer the architect related questions, but we definitely will take them forward to Neil and David, or you can always email those questions to either LCBT Gateway or Edinburgh Napier University, and we definitely will address them if you are too shy to ask them straight away at this webinar. But whilst they're waiting for questions to come, I would like to ask Deb on, so I understand from the presentation that so you are trying to use only the homegrown timber. Is that one of the aims of your research, is just to focus on the homegrown timber rather than import timber and just build up from that?
Yes, the premise for doing the research was through the Wood Products Innovation Gateway, and that specifically provides funding for small and medium enterprises to encourage the use of homegrown Scottish timber, yes.
So you mentioned Wood Product Innovation Gateway, just to make it a little bit clear for those who don't know what it is. It's another project run by Edinburgh Napier University, also helping the Scottish companies to develop products out of local wood, and LCBT Gateway as such is partnering with Wood Product Innovation Gateway everywhere where we could. So it's a good example of work which actually going across not a single project but a few. The other question would be came from Craig Bishop here from Kickstart Online, is on how many examples are here in Scotland for use of this timber, and actually had exactly the same question or similar question to what are those combinations of nail lamb or double lamb, where are they used, and what are the applications for them?
There are some buildings made of dowel lamb, but they've all been imported from Austria to date. There's a school in Acharacal over in Ardnamurchan, and there's also a house down in the Borders. But I think to date there's only been one building which has actually included any of these products made with Scottish timber, and that's David Blakey had used some of this material in a house. I'm not exactly sure where, but I'm sure David would explain if he was here.
Okay, the next question is about the timber. So the timber comes, I believe, from the sawmill. So at what degree these timber planks are prepared, before they're going into the drilling procedure and press? This is a question from Keith Pierce.
For the nail lamb, the timbers were planed timbers, just because that's how we got them from the sawmill, and they were already milled. In terms of the dowel lamb, the sideboards, these were purely just sawn timber, so so they weren't very smooth. There was actually quite a lot of differences in height on the panel itself, across the width of the panel. So you can actually use them rough like that, but only in an industrial situation. If you're wanting to put them into a building, you'd want to have at least some sort of regularisation. And on the next set of tests, we're actually going to have them planed so that we get less localised crushing, for instance, when we're looking at the bending stiffness.
Okay, couple of questions. Actually, quite a couple of people are questioning about the treatment for the timber which is required, which Deb just answered. Another question is about certification. Is this timber actually, sustainable? Does it come through any certification process, like using Certisource?
I think the timber that we obtained from the sawmills for the nail lamb testing is partly certified. I can't quite say for certain on that one. And as regards the timber that we obtained for the dowel lamb testing, that was produced from Neil's own timber, and I don't know exactly what sort of certification he's got. I'm afraid you would have to ask Neil that one.
Okay. So have you got any plans of comparing the different nail and the dowel laminate elements to, say, for example, the more known glue lamb or cross lamb things or equivalent products in your future research?
Hadn't thought of that, because of course when we tend to think of glue lamb, you tend to think of beams rather than flat panels, although they are, I'm sure they're available, but we were looking at sort of lower technology with this, but it could be quite interesting to see how a glue lamb panel would be equivalent. That would certainly be something to think about.
Okay, again, it's another question about comparison with cross lam. So one of the benefits of cross laminated timber is its fire resistant capability. Did you do any testing on fire resistance for your nailed and doweled systems, or are you planning to do any?
It compares in the same way, in fact, that it's solid timber, and therefore the charring rate is going to be the same. CLT actually, because of the glue line, there are it's not quite, I don't think, the full just straightforward charring rate, and there would be implications, of course, if you've got the nail systems, but then the nails are set back from the surface, so it would still just be the charring rate. I think in terms of fire design, it's a question of either protecting it or engineering it in terms of charring, but that's a bigger issue, and it's something that in terms of the structural aspects, we in the centre can't look at that at the moment, but I know it's a big issue in terms of the fire performance.
Okay. Whilst we're waiting for any further questions, I've got another one for you, Deb. I believe all those construction tested have been done of the same type of timber each. So you did compare dowel plank, for example, made of different types of timber, but it was the same pieces of timber in each. Is there any? Is it important that it's the same timber, that the same Sitka spruce in the whole thing, or could it be layers of different timber?
I think you'd want to stick to the same species of timber for any particular panel or even a particular product, really. What you could do, of course, is change the visual quality if you wanted to have it exposed, and pick a different timber, but it would have to be for the whole wall because it's a structural element and not just cladding.
Not just like cosmetic.
No, no.
Yeah, it's structural, which is more important. So I believe you have done a lot of measurement and technical analysis, but have you done any economic analysis of that, like comparing what is the difference in cost of building of the lamb or an lamb versus the standard timber construction? It could be a question actually for the architect.
I know Neil at Macar has done some work on this, and yes, he did find that it was a bit more expensive. If I remember right, it was the two numbers he had was 2,600. I can't remember whether it was thousands or what, or per panel or what, but it was 26 versus sort of 31 for the dowel lamb. But this is using, you know, very crude equipment at the moment compared to having you know, been making timber frame panels for a long time, which he thinks he should be able to get some economies with practice or with improvements in his manufacturing system. But it's not just a question of the price of a bit of wall, it's to do with the building performance as well, which is, I'm sure, is what he'd say, but we haven't actually looked specifically at the moment at different costings, either between nail lamb or dowel lamb.
Okay. Another question, I know you ran through this at your report, but can you quickly summarize for us, so in comparison with tests tests done in Europe, for example, did you compare your measurements with similar materials tested in Europe, or you did not?
No, the comparison with the racking test, we just compared with the open panel that we had here.
Okay. And also, I believe in Europe they're using different type of timber anyway, so it's difficult to compare one type of timber to another anyway. There's another question about the density of timber. It's the variability in density of timber from various species has large effect on the structural strength of the panels.
Yes, you could see that the Scots pine was stronger than the Sitka spruce, and all timbers have different strength properties. It's a question of whether you put them into a structural grade, which is typical. So you might find, particularly with Scots pine, you'd actually be able to reach a stronger grade if you wanted to have a strength graded timber than you would if you used a smaller timber. But in terms of strength, the panels are so massive that the strength would rarely come into it in terms of a domestic sort of scale, and it's the stiffness that would limit, and some would give you a stiffer floor than another if you wanted to be more specific in terms of choosing a species.
So I believe if you use if you want to use those panels for walls or for flooring, it could be different products specified, but in general they all tested to be structurally strong.
Yes.
Okay. What is the typical or average weight of the panel size when you produce it? You know, does it have to be lifted by crane?
Yes, the typical width of panel would be 600 millimetres, just because of, you know, getting the dowels inserted into them, because they have to go through the whole lot at once. So a typical weight for each individual panel would be a couple of 100 kilos. So all the handling does have to be done with gantries and hand-controlled lifting gear. But in terms of that, would be comparing to a closed panel situation, you'd be doing that with mechanical lifting gear as well anyway. So yes, all the panels do need craneage, even within the factory and on site.
Okay, thank you very much, Deb. I've got another question for you. Let's see. It's a question from George, who's saying that there are other projects at the moment in Wales using homegrown timber. Do you aware of different projects going around UK on that? I believe you want to comment on that, like.
Yes, I'm very sorry for missing you out. I was aware of this, and in fact, I'm hoping to visit it next month. And we've heard good reports back, and very good to hear that it's going well. We just feel a bit of a shame that we've been pipped to the post by the Welsh. But excellent, it's really good news.
Yes, and also I believe in Scotland that's the project. Nobody else is doing this type of systems in Scotland at the moment. You are pioneering in that.
There's a couple of people looking at setting up a Dale Lamb place, other than Neil already, but he hasn't actually started incorporating it into his designs as yet. But we've had a lot of interest, particularly from the seminar we had 2 days ago. And there are other people, there's people in Sussex and in Cornwall also looking at the economics of setting up a Dale Lamb fabrication centre.
Okay, there is another question here about E-Core. I don't know, Deb, if you would be able to answer that. It's during the structural design of E-Core, did you use the test results for walls of the core? Or how was this material chosen? Because I remember this E-Core from reasonably very beginning. There were different materials trialed. So did the choice of nail was because of its structural properties? Or?
Part of it was its properties, but part of it as well was looking at actually using living solutions as well for the community. The organisation itself, and therefore we had to pick the material that seemed best suited for the capabilities there, and it worked very well. We were able to use some of the test results in terms of the racking to satisfy the checking engineers that they were happy that it was going to perform. So it was all checked over.
Okay. I have a very lengthy comment. It does look more like a comment rather than a question. It's actually talking about the first brass staple house here in Scotland from John Fial, and it's talking about, it's quite difficult to summarize that long one, but energy of the first brass staple house in Scotland which came from Austria, I believe, used 40% moisture and 8% hardwood dowels, and the idea is.
God, there's 5 questions there.
Yeah, it's a long one. So, Deb, would you be able to, break it down into answers where you could, or just? Yeah, so we're talking about humidity first to avoid thermal moisture conditions resulting in potential different reactions in the material when it's in use. Oh my goodness, that's a long one. It would be nice to have 4 different entries if it's individual questions rather than one very long.
I mean, yes, in terms of the moisture content chosen, there's 14%. Obviously, it is going to dry down a little bit more in service, but obviously the difficulty is if they get wet, yes, and I think part of that must come down to how it's handled in transport and how they're built. If they do get very wet, then they will swell and it could cause an issue, but then it comes down to anything. It's by using off-site methods and possibly even then more finishing that you can do off-site, then the less exposure there is to the weather. But yes, it is an issue to think about.
The second question is about environmental moisture. So actually, it's kind of saying in the promotion of those houses that it will absorb the moisture and then return it back to environment, but does it not create like mold growing inside?
That's a building performance issue that we haven't addressed in our structural work at all. But yes, I know one of the selling point is the fact that this hygrothermal movement, and it's something that is definitely a good point to think about, and I think that's why it's sold. But I'm not really qualified to talk about the hydrothermal performance of timber, unfortunately.
Yeah, okay. And then number 3 would be about quantity of indigenous timber required when it's introduced into well, probably larger construction. So do we have enough of timber, to go for it?
The Forestry Commission in Scotland is actively trying to increase the forest cover in Scotland, and also I know that's down the line if they plant sort of now, but there are increasing supplies coming onto the market of Scottish timber, and we've conducted various research in terms of the availability of timber in case a CLT plant would be viable, which of course uses a similar, if not more, amount of timber, and the conclusions are that there is sufficient timber within Scotland that it would be able to be used.
Okay. And the number 4 here, which is probably also out of interest, is of course, if your timber is delivered from Scotland to the Scottish plant, it's probably reducing the carbon footprint of the entire, building manufactured, but it's actually increased, carbon footprint because you produce the production process is quite energy, costing, or is it not?
I'm not sure whether you're saying that the embodied energy is a higher input than in a timber framed house with an open stud framework. I'm afraid I don't know the answer to that one. That's something that a life cycle assessment would be interesting to do.
Yeah, it's difficult to get the understanding of the 5th one. For me, I don't know. So I'll just go to the next question, and if John wants to, add a little bit more into that question, you're more than welcome to resubmit it, the number 5, because it's very short, isn't it? But Craig Bishop is asking, are there any implications to the health of occupants comparing to the blue houses, like ventilation, etc., or you didn't look into that? And that's more.
Well, I do know that the glue methods, the issues of VOCs, it's very, very small, and but of course there wouldn't be any at all with the nail or a dowel system, because there isn't any glue. So it's just the natural wood itself. So. I'm afraid, again, yeah. I'm a structural engineer.
Yeah, it's probably more a question to builders, so,
on building performance.
To the building performance, so it's more a question to Neil, because he's, Sutherland is not only the architect, but also they're building houses through Makars, so they probably would be able to answer that question. Have you tested, have you tested the reabsorption of moisture if the panel are left outside? I think you've touched on that already, but knowing the weather in Scotland is as such, I know that the best way of reducing the amount of reabsorption is actually delivered quickly and build and cover. But can you comment any more on that? Because it's absolutely critical.
Yes, I would agree with that, but then some timbers reabsorb moisture quicker than others, and Scots pine is maybe not the best one. Sitka spruce is very good in that respect, and doesn't reabsorb the water as quickly, so it's a bit more forgiving in terms of situations like that. But with all these solid wood systems, yes, it's you have to pay more attention to to construction and protection of the timber during construction.
Okay, that was so far the last question, and I think we should probably wrap up here and thank Deb and thank Kickstart Online for helping us to organize this event. And there are going to be another 2 webinars run in this collaboration between LCBT Gateway and Kickstart Online in the near future, and I believe you either already received or will receive invitations for those, touching on other projects which we run in this project. And I hope to see all of you again, and thank you very much and goodbye.